Hi, this is Dr. Harris, and this is my first attempt at creating a video with content for Math 125 Calculus 1. I'm sure I'm going to be a little bit rusty at first. I'm probably going to make some typing errors, but just bear with me. We're going to see how this goes, and just try to take in what I'm getting at. Remember, on the last day of class, before the break, we introduced the chain rule for calculating derivatives. And at the top of the screen here, you can see that I've got the formula for the chain rule. The derivative of a composition of functions is the derivative of the outside function composed with the inside times the derivative of the inside function. So we recall that it's vital when we're looking at an expression to be able to determine what the inside and outside functions are. So I've got four examples for us here. They're on the handout that I passed out back on the last day of class before the break. And so if you have those and you've tried them, you can compare what you did in your practice with what I'm about to do here. So let's look at these four examples. The first one is m of x is equal to the cosecant of e to the x. And so the first task is to correctly identify which functions are outside and inside. So here we can hopefully see that e to the x is inside the cosecant function. And so therefore e to the x is going to be the inside function here, and the cosecant function is going to be on the outside. So in order to apply the chain rule, we have to know the derivative of both the inside and the outside functions. And so I've got them written over here to the right. In this case, the derivative of the outside function, the cosecant function, is minus cosecant x cotangent x. And the derivative of the inside function, e to the x, recall, is simply e to the x. So let's see how we put this together. Hopefully this will look familiar to you if you were in class beforehand. If not, hopefully you're getting some, you've been able to read the text, get a bit of a feel for this. But let's try to put this together. So the derivative in this case, according to the chain rule, is going to be the derivative of the outside function. So it's going to be minus cosecant. And I'm going to leave the inside function alone. So it's going to be minus cosecant cotangent. And what we do is we put the inside function in here. So it's going to be minus cosecant, and then I'm going to insert e to the x here, and I do the same here. So that's the derivative of the outside function evaluated at the inside function, and then we multiply that by the derivative of the inside function. And so we can just type in e to the x as the derivative of the inside function here. And so the answer in this case is going to be m prime of x is minus cosecant of e to the x times cotangent of e to the x times e to the x. Again, one of the things mistakes that's easiest to make in a situation like this is to forget that cosecant and cotangent are both functions, and so it's minus cosecant of the inside times cotangent of the inside. Moving down to the second example, then here we've got a sum of functions, y equals cotangent cubed of x plus cotangent of x cubed. And we want to recognize that each of these parts in the sum is a composition in and of itself. And what's happening is that the two functions that are involved in the composition in both cases are the same, but the role of inside and outside function has changed. In the first function, cotangent cubed x, what we want to recognize is that we're applying the cotangent function first and then cubing it. And so the inside part on the first term is cotangent x. The outside part on the first term is x cubed. Whereas in cotangent of x cubed, we have the reverse. X cubed comes first, followed by the cotangent function. And so the inside part on the second term is x cubed. The outside function is cotangent x. So in both cases, we're going to need to remember what the derivative of the cotangent function is and what the derivative of x cubed is. I've got that over here. This is something that you've got to bring with you to the problem. And so for the first part then, the derivative of the outside is 3 something squared. We have to fill in the something in a bit. And so what goes inside is the inside function. And so if the inside function is cotangent x, it's going to be 3 cotangent of x squared times the derivative of the inside function, which in this case is minus cosecant squared x. And then we're going to add to that the derivative of the second term. And here then, we take the derivative of the outside part, which is in this case the minus cosecant squared. And so we'll be inserting that. And then we'll leave a blank there because it's minus cosecant squared of the inside function, which in this case is x cubed. In the wrong place. And then we multiply that by the derivative of the inside function, which is 3x squared. And so this is our answer to this problem. So let's go over it again real quickly. The derivative of the first part is 3 times the inside function squared times the derivative of the inside function. So it's 3 cotangent squared x times minus cosecant squared x, and then plus the derivative of the second part, but I'll put a minus here because the derivative of the cotangent function is minus cosecant squared of the inside function. So I get minus cosecant squared of x cubed times the derivative of the inside function, 3x squared. Let's move down to the third function. So f of x is 3x plus 1 over x minus 3 all to the fifth power. This is one of those cases I mentioned in class a week and a half ago where what we've got is we're going to have a combination of the chain rule, and to take the derivative of the inside part, we're going to have to use the quotient rule since the inside part is a quotient. And so what's inside is the quotient 3x plus 1 over x minus 3, and then we're raising all that to the fifth power, so x to the fifth is our outside function. Over here, I've got the derivative of the outside function, and then I've applied the quotient rule to get the derivative of the inside function, and I've simplified that to minus 10 over x minus 3 squared. And so our derivative then is going to be the derivative of the outside, 5 times something to the fourth power, and that something is the inside function. And then we multiply that by the derivative of the inside function, which is this work I've done over here on the side in advance. And so here, the derivative is 5, the inside part to the fourth, times the derivative of the inside function. Lastly here, number 4, I've got the square root of sine x times cosine x. And so we were first taking the product, sine x times cosine x is my inside function, and then I'm applying the square root to that, so the outside function is the square root of x. Recall that the derivative of the square root function, the square root of x is 1 over 2 square root of x. And then the inside function is a product, so I'm going to use the product rule. Remember, the derivative of the sine function is cosine. The derivative of sine x is cosine x. The derivative of cosine x is minus sine x. And so when I apply the product rule, I get the derivative of the first times the second plus the first times the derivative of the second, and I can simplify that to cosine squared x minus sine squared x. So therefore, when it comes to taking the derivative of this function, my answer is going to be the derivative of the outside. And so I'm going to have 1 over 2 times the square root of the inside function. Let's come down here. And I'm going to multiply that by the derivative of the inside function. And since that's a sum, I'll need to include this in parentheses. And so I get as my answer 1 over 2 times the inside. So 1 over 2 square root of the inside. So 1 over 2 times the square root of sine x cosine x times the derivative of the inside function, which is cosine squared x minus sine squared x.